I'm Preetha Appan, and I work on the Nomad team at HashiCorp. And today I'm going to be talking about a recent feature that we added to the Nomad Scheduler called Preemption, and just more of a technical deep dive um, for how it works. So if you're just tuning in or you're like super new to Nomad, I'd still like to go through a few introduction slides just for anyone in the audience that isn't familiar with Nomad. So Nomad is a cluster orchestrator. It's in the same, it operates in the same problem space as some of these other projects that you might be familiar with, such as Kubernetes, Apache Mesos, Docker Swarm, Hadoop Yarn, etc. And the core purpose of an orchestrator is to map work to resources. So given a set of workloads or jobs that you want to run and some compute capacity that you have, the orchestrator is responsible for figuring out the best compute node that it can run your workloads on, but also for continuously monitoring them, handling failures if something fails, trying to place it on another node, or if there's a network failure on a specific node, then like moving all the workloads that was running there to another place, so that you don't have a human or people getting paged when things stop working. So that's why people use orchestrators. There are a few ways in which Nomad is different. Our emphasis is on workflows and not technologies. So Nomad supports containers. You can run Docker workloads, but you can also run legacy applications in Nomad. In Nomad 09, which we shipped a beta release at the end of January, we support pluggable drivers. So you can bring your own runtime if the existing set of driver runtimes don't meet your use case. It's easy to use. There is a single binary, that's it. And there is no external state store or external dependency. It's built into the Nomad server. We really emphasize scalability and performance. So we've seen Nomad run successfully on 10,000 plus nodes. Now it's been a while since we benchmarked Nomad, but the last time we benchmarked it, it was able to make 5,500 placements in a second. Nomad is composable. It's the runtime layer of the Hashi stack. So it's what's responsible for running your services and applications. But it integrates with Vault for secret management and container secret injection. You can use Terraform, HashiCorp's Terraform, to provision the compute infrastructure that Nomad would run applications on. Wrong slide. And then Nomad also integrates with Console. So Nomad uses Console for service discovery, service registration, as well as service mesh capabilities. Also, Nomad can find each other through with HashiTalks, a lot of things there that go fun on top of nodes, such as like continuous deployment, maybe looking at a tree, then triggering integrating with your CI/CD system to be able to trigger deploys of new versions of your application. Auto scaling is another use case, and then also just metric dashboards, like monitoring the metrics that Nomad spits out and building your own dashboards on top of it. Nomad is flexible. So it works on multiple operating systems, Linux, macOS, and Windows. We have a lot of people using Nomad in Windows today. It's also flexible in the runtime layer, like I said, with driver plugins. These are some built-in ones that ship with Nomad, like QEMU is a VM, Docker containers, Rocket is a different type of container technology, and you can run Java apps on it, but you can also bring your own as of Nomad 09. The basic unit in which people interact with Nomad, or developers or operators interact with Nomad, is through what we call a job file. This is a job file in HCL, or HashiCorp config language. The Nomad API also supports JSON version of this. But the most simple or basic job file will contain information about how you want Nomad to, about what you want Nomad to run. So, what's the type of workload, what data centers you want it running on, how many instances you want, that's the count equals 5. And then the idea is that the job file is a logical unit in which you can describe different types of groups in it. So a single job can have multiple groups, and then everything that runs inside that group. So a group can have multiple tasks, but everything in that group is usually co-scheduled or co-located on the same node. So that's just a brief introduction about Nomad, but my talk is really going to focus on the scheduler, and a very recent feature that we added to the scheduler. But before we do that, I want to just introduce the scheduler in a little bit more detail. The primary purpose of the Nomad scheduler is to assign tasks to client machines. So the way it does that is by using a bin packing algorithm that optimizes for resource utilization. It also respects any placement constraints that you have. So for example, if you have a mix of both Windows nodes and Linux nodes or in your cluster and you want a specific job to only run on the Windows node, or you wanted to use a specific GPU, then the scheduler respects all of those things when it's assigning tasks to run on a specific client machine or client node. I mentioned bin packing. So bin packing is basically the core placement algorithm that the scheduler uses. I like to use a good real world analogy when explaining bin packing. So consider this pantry box. It has a certain fixed capacity, and then we have all these different snacks of different shapes and sizes. Some of them come in boxes, some of them come in packets. But we have made optimal use of the available capacity in this box by like packing all the individual snacks a certain way. So the same concept, but applied to a machine with a certain or a compute node with a certain amount of capacity. It's got this much RAM, this much disk, and this much CPU cores, and it's got these GPU devices and so on. So we have all that information. So that's the box, and then the snacks are like your applications. So what are the different applications that you want to run inside that node, and what's the right way to pack them in so that we're optimally utilizing the compute capacity. Another important detail about how the scheduler works is that it's a priority-based scheduler. So that means that every job specifies a certain priority. The priorities can range from 0 to 100. And the scheduler is going to process any incoming placement requests in priority order. So if it gets 2 requests, one of priority 20 and one of priority 100 at roughly the same time, it will first place the priority 100 workload before it places the priority 20 workload. There's a problem with, there's a known problem with purely priority-based schedulers, which is called as priority inversion. It's a situation where a lower priority task inadvertently prevents placement of a higher priority task. That sounds a little abstract, so I'm going to walk through a real example to describe how this might happen. So let's say you started out with a bunch of compute nodes, like they're colored in green on the left because green just means available. And then, this is my company. I'm running apps on Nomad. The first thing that I want to do is I want to run my very business critical front-end app because that's how users come and use my product. And it's a priority 90, and I want 5 instances of it. It's a Docker container. We're just running the web front-end. Okay, great. So that's fine. So that takes up some amount of compute in your cluster. You still have plenty available. Now you need to run your payment service, which again, that's how you're charging people to buy your product so that they can buy your product. It's super business critical. We need some additional compute capacity to place that. It's also very high priority, and so we run that. But that takes up some more room. Then after that, now you start getting user traffic. People are clicking on different parts of your site, and maybe you want to run an analytics workload. This is not in the critical path. It can be done offline. Some background process or a batch job that's looking at click data and trying to and do some analysis, do some reporting. So that would be a lower priority workload. So that's a priority 20, but we need a lot of those, like we need 25 of those. So we take up some more room in the cluster. Then you have the marketing team. They want to run email marketing campaigns. Again, that's a lower priority workload, priority 20. So you run that. So that takes up some more capacity. Then eventually you have a data science team. The data science team wants to build models and it's using some neural network learning algorithm or something like that. It needs a lot of instances, 200 instances, because it's highly parallelized. But it's a very low priority task because it's okay if it takes long or but again, it's not in the critical path. So we run that, and then that takes up the remaining room in the cluster. So all of this is fine, and we process them in priority order as they came into the scheduler. But at this point, the cluster is basically out of capacity. Now let's say that you actually got more traffic, like the app became viral, or lots of people started using it. So we want to increase the number of instances from 5 to 10. And we do that, and it turns out that we don't have capacity in the cluster anymore. That's basically what's called priority inversion. So we have two options when we run into this situation. We could either add more capacity, which you can do manually, get a sysadmin or a cluster operator on the phone and have them do it for you. That's going to take a few minutes. You could also add capacity automatically through things like auto-scaling groups if you're running on a cloud provider. But even that takes a few seconds. It's not going to be instantaneous. So that's one option. The second option is that you could actually make something else that's running give up its used capacity in order to place this higher priority workload. That's basically what preemption is. So preemption is a process by which the scheduler makes room for a higher priority workload by finding lower priority workloads to evict. So to take a more visual example, so on the left, we have this priority 70 workload. It's requiring certain resources. It needs 1 gigabyte of RAM, 2 CPU cores, and 1 gigabyte of disk. And then on the right, we have a node where we're trying to place this, but that node looks pretty full. The colors in this diagram just represent priorities. So things that have the same color have the same priority. And because these are applications that are all slightly different, right? Like they consume different types of resources, that's why they just have different shapes. So the shape just is a rough indicator of how much capacity they're using. Before we jump into how preemption works or the implementation details, let's talk about some considerations. What are some things that we needed to think about as we were implementing preemption? What are the things that we need to consider? The first thing is that we have to look at what is the workload requirement. So the thing that we're trying to place, what does it need? That's super important. We need to look at the resource utilization of the running jobs. So like I showed in the previous slide, we have, each one is slightly different shape. They use different amounts of memory, disk, and CPU. We also need to consider the priorities of those running jobs. They can be anywhere from 0 to 100, but they clearly have ordering, some of them are more important than the others. We also need to look at the number of instances of the ones that are running. So for example, if you had, in the business critical example that I gave, if say we had a different kind of payment service, like maybe an invoice service that was not super business critical, but it was priority 50, and there were 5 instances of those running. Should we really preempt all 5 of them? Because then you're left with no capacity, right? So you want to make sure that when you're preempting, you don't preempt too much of the same type of job. So that's another consideration. And then another important consideration is just avoiding wasting resources, because again, we want to find the best fit. Sort of like Goldilocks and her porridge. It shouldn't be too much. It shouldn't be too little. It needs to be just right. So at a high level, we collapse preemption into 2 high-level problems. The first is intra-node allocation selection. So within a particular node where we're trying to place something, and there's a bunch of allocations or running tasks, what's the subset that we need to pick for preemption? So that's one high-level problem. The second high-level problem is inter-node scoring. So if you have more than one eligible node and each of them have a different combination of things that can be preempted, how do you compare and score across them? So those are the two high-level problems. I'll start by diving into the first one, which is intranode allocation selection algorithm. The first thing is we need to understand assumptions or invariants. So what are some things that we absolutely have to guarantee? And the first one is job priority. So the whole point of even doing preemption is to prevent priority inversion. So that means that preemption should never preempt a higher priority workload in order to place a lower priority workload. So that's absolutely a table stake here. The second invariant or set of invariants are just what I call static requirements. So sometimes in Nomad, like you can either let Nomad allocate a port based on available ports, but you can also hard code a port, for example. For legacy reasons, you might always want a certain app to run on port 80, and you can specify that. Or you want a very specific host, like this is the only host where this app can run on because it needs some other dependency that only lives there, things like that. So those are static requirements. And when preempting, we must always meet those static requirements because they're another kind of table stake. So to go back to our example here, so I've just, the A just means as a short form for allocation. So we have, this particular node, it's got 10 different allocations. Each one is using different amounts of compute. And we're trying to place this specific allocation. So a naive way to do this is to just go through all the different options. So how do we do that? We could actually list every possible subset of allocations running on that node. It turns out that when you have n elements like that, there are 2 power n different subsets. And then we could go ahead and assign scores for each possible option based on how well they fit the requirement that we're trying to fill. And so this gets expensive really quickly. So even with just 32 running tasks, like you have 4 billion, 2 to the power 32 or 4 billion different combinations that needed to be scored. So it's too expensive. We obviously didn't do that. A key insight we had is that we don't actually need to examine every single allocation. The priority is a very reasonable way to bucket things. So we could look at things by, things that have very similar priorities. So in this example, these 2 greens have the lowest possible priority among the ones that are running on that node. And so we could start by looking at those 2, we consider them for preemption. And then we could go to the next highest one, and then the next highest one, and so on. Another insight is that we don't need to examine every single thing. We can actually do it in an iterative manner. We stop when our requirements are met. So let's say we examine 3 different sets of allocations, each with a different priority. At this point, we've met all our requirements. We can stop. Let me just do a time check. Okay, yeah, I have time. The other insight we had was that we need a reasonable way to compare these very disparate workloads. So on the one hand, you have the thing that we're trying to place, which is on the left. And then on the right side, it's something that's already running. This one's providing 1 GB RAM, 1 CPU core, 4 GB disk. I've simplified it by only showing 3 dimensions, but there's actually, it's a multi-dimensional space. You also have network, you have devices. In the future, we might add IOPS again, so that's another dimension. So we need a way to come up, to compare these 2 and come up with a distance function in order to figure out how close they are or how far apart they are. The distance function that we ended up implementing uses this formula for each dimension. Now, I'm not going into too much details here, but for a single dimension, it's simply needed minus used divided by needed. But we combine, we calculate it in a Euclidean space and do Euclidean or sum of squares distance across multiple dimensions. It ranges from -∞ to 1. With the idea being that 0 is best fit. So if you need 1 CPU core and by preempting this thing you get 1 CPU core, then according to this formula the distance is 0, so it's the best fit. And if you notice if you're using more than what you need, then you're going to get a negative score with this. So this means that in our approach, supersets are somewhat penalized because one of the considerations we had was avoiding wastage. This is how the overall iterative algorithm works. So the first insight, which is you can group things by priority, and then within each group, you sort by distance, using the distance function that I mentioned in the previous slide, and you go from lowest to highest distance. And then within each group, the iterative algorithm just adds adds it to a running set. And then at each step, it checks whether requirements have been met. So I've preempted one thing, have the requirements been met? Or I'm considering preempting one thing, have the requirements been met? Okay, they've been met, then I can exit. If not, you go to the next element and so on. And then our algorithm also has a final filtering step where we remove any unnecessary candidates in the final set. It's a little abstract, so again, I want to use a visualization to talk about how it works. So in this particular way of thinking about it, you have a two-dimensional space. The x-axis is the distance from requirements. Like I said, it ranges. We use sum of squares, so even though each individual dimension ranges from -infinity to 1, through sum of squares, it actually goes from 0 to infinity. So you have a distance that starts all the way from 0 to infinity on the x-axis, and then you have priorities which go from 0 to 100. And then we're just placing all these workloads, running workloads in that 2D space. So the first thing we need to do is meet static requirements. So let's say in this example, the job author said that they need port 5656 and allocation A10, which is actually pretty far away from the requirements. It's 2.8, but it's using port 5656. Because it's an invariant, we do have to choose A10. So we do that. And then after that, though, like once all the static requirements are met, we start from the lower left corner of this graph. So we start with the lowest possible distance and lowest possible priority that we have. So we select A1 for preemption and see whether our requirements have been met. Okay, they haven't been met. So now the search space moves further to the left on the x-axis. So we look at A2, which has the same priority, but a little further distance away. And then we look at A3 and so on. And then at this point, we've exhausted everything on that have the same priority. So we move to the next highest priority that we have, which is A4. And then here we're like, okay, we have enough. At this point, the iterative algorithm is like, okay, I've met all the requirements. I'm going to stop. So that's just the first 3 steps, though. And then the last step, which is again really important, is to remove unnecessary candidates. So in our example, we ended up with these 5 different things that we decided that we needed to preempt. But then that last step would actually filter out A1 and A2 because it determines that A3 subsumes A1 and A2. So again, to understand that visually, because our algorithm starts by adding subsets of nodes of running tasks that fulfill the requirements. For example, say we needed 4 CPU cores. We get 1 core from A1 and we get 1 core from A2. We still need 2 more cores. The next highest thing that's running on the node is A3, but it actually turns out that A3 is using 4 cores. So we select A3, but at this point, we actually no longer need A1 and A2. Because A3 completely subsumes A1 and A2, so we can eliminate that. So that's why we have that final filtering step. So in a nutshell, the summary is that we started out trying to place this priority 70 allocation, which had these certain requirements, and then we followed this iterative algorithm. It was able to preempt 2 priority 10s and 1 priority 15. And at that point, it terminated because it was able to complete the requirements. So far, what I've explained is just the first step, which is intra-node allocation selection. So within a particular node, how do we figure out what subset of those allocations do we need for preemption? That's fine, but at a high level, we also have another problem, which is inter-node scoring. Why do we even need internode scoring? So we need that when there's more than one eligible node with preemptible allocations. So for example, if you're running a batch workload or a service workload, in general, you have more than one possible node in which that workload can run, unless the workload is heavily constrained. Like it says something like, it needs to run on a Windows node with like this specific device, and for whatever reason, in all of your cluster, you only have one node that meets that requirement. That's fairly rare though. For the most part, it does, usually for placing batch workloads or service workloads, you have more than one node. So that means that we also needed to solve internode scoring. So to kind of zoom out from where we were talking about selecting running tasks on a particular node, we might have 4 different eligible nodes to place this workload. And each one of them might yield a different combination of things that could be preempted. And we still need to place this, this incoming workload. So which one do we choose amongst these 4? So that's what the internode scoring problem is. I won't go into too much detail into how we implemented that because there's actually so many different ways to do it. And we picked the approach that we took is based on the priority of the combination of preemptible ALECs in it. So it tries to minimize the priority of the combination of the preemptible ALECs in each particular node choice that we have. Another important thing is like it's not the only consideration. So the way our scheduler works is it looks at bin packing. It may look at preemption score. If the job has affinities, which is a new feature that we added in 0.9, like you might have an affinity to run on a specific data center or use a specific GPU, then it takes that into account as well. So it takes all that and combines that to come up with a final score for placement. So in our concrete example, we may end up assigning scores like the first node running A1, A25, and A4 gets a score of 0.9, the other one gets 0.02, and so on. And the node with the highest preemption score is the first one with the 0.9. Now, for the most part, all of this is just going to happen under the covers. It just works. But we have implemented or provided some additional visibility if operators want to debug like why their lower priority workload stopped running. And we do that by adding 2 new fields to Nomad's allocation API. So the job that causes preemption, any of its running instances or allocations will have the preempted ALEX field set. And it'll be a list of allocation IDs of the things that it preempted in order to place this. And then we also do it backwards. So preempted by alloc ID. So anything that got preempted by the scheduler is going to have a new field in it with pointing backwards to the workload that preempted it. We've also integrated it with Nomad Plan. Nomad Plan is basically doing a dry run of the scheduler. It's useful for it's used in CI/CD environments, for example, to make sure that you have enough capacity. So it doesn't actually place anything, but it dry runs it and gives you the output. And so it's a very point-in-time output. So if you run it again, an hour later, the value might change because it might have found a better combination. But basically, it shows you if placing this workload is going to cause any preemptions, then it shows you the details of what it's going to preempt. In terms of the rollout of this feature, so Nomad OSS, which we shipped a beta release for in January of last month, ships with preemption for system jobs. And then Nomad Enterprise is going to have preemption for batch and service jobs, and it's coming in 0.91, which will be probably April. With preemption, you can, the core purpose of preemption is to keep your business critical apps running without any intervention. And that's all I had.